Well, hello guys. Welcome back to my channel Gamma Di Gamma. Today I'll be doing some questions of limits. Last time we'd done, the concept of limits. I gave you an intuitive understanding. So, in this video we're going to try to apply the concept. So before we start doing any questions, I would like to write down certain limit properties. The first one is the limit as x approaches, say, plus or minus infinity of a function f of x. Let that be equal to L, and the limit as x approaches plus or minus infinity, say g of x equal capital M. Now the first property goes like this: if we have the limit as x approaches plus or minus infinity of f of x plus g of x. Guys, let me remind you, it's a healthy practice to put brackets like this, is equal to L plus M. So basically you can separate, take limit with only f, add it with limit with only g, same as taking the limit on the entire sum of functions. And as you might have suspected, it's the same thing with subtraction also. So f of x minus g of x is equal to L minus M. And the great thing is that you can also do it with products of functions. So if you have f of x times the g of x, it's L times M. And yeah, you can also do it with dividing functions. When you have if you have, say, f of x over g of x, you'll get m over n, where of course m won't be equal to 0, because then if we started with a rational function, it should not be undefined. And there's another special property, probably like you can call it like an identity. So say you have limit as h approaches 0 of sine of h over h. This will just be equal to 1. And similarly, if you have the limit as h approaches 0 of the tangent of h over h, even this is 1. Now, for those of you who require a graphical intuition, let me draw its graph. So let me draw the graph of sine of x over x. Yeah, so this is what the graph of the sine of, say, x over x looks like. And you might have guessed there is a discontinuity at x is equal to 0, because it simply gets undefined, but the limit still exists, because if you look at this, pass a line through it, this line is x is equal to 1. So from approximating from the information we have around this point, when this approaches 0, when this function approaches 0, the limit is 1. And a similar logic follows for the tangent of h over f, over tangent of h over h. And for some of you that have done physics in the past, you might know that in physics sometimes we assume that sine of x is almost equal to x for very small x values. So even by that intuition, this limit makes sense, this limit identity makes sense. Okay, so today, first we're gonna do rational limits of rational function. So I have this example: limit as x tends to infinity of 5x squared plus 8x minus 3 over 3x squared plus 2. Now what you want to do as you proceed with the question is you want to divide the numerator and denominator by the highest degree term, and that in this case is x squared. So let me go ahead and do that. 5x squared divided by x squared is just 5. This will be 8 over x minus 3 over x squared all over 3 plus 2 over x squared. Now since x is tending to infinity, now this fraction, the denominator is getting really large, so this is going to tend to 0. It's going to become really small. Same with this thing. I mean, all the terms which have an x in the denominator, all the fractions that have x or power of x as x tends to infinity are going to go up to 0. So all we are left with are these constants like 5 and 3. So the answer is 5 by 3. Now I would like to do another example. So the limit as x tends to negative infinity of 11x plus 2 over 2x cubed minus 1. Now we're going to divide by the highest degree term, and here it's x cubed. So our question becomes limit as x tends to negative infinity of 11 over x squared plus 2 over x cubed over 2 minus 1 over x cubed. And as x tends to negative infinity, this thing will go to 0. I mean, all the terms which have an x in the denominator will go to 0. All we are left is half. Now in these type of questions, it doesn't matter if it's positive infinity or negative infinity. I mean, it's getting really large. The denominator is getting really large in this fraction. I mean, really large negative or really large positive doesn't matter, because finally if the denominator is really large, the entire fraction will tend to 0. That's what happened in both of these examples. Now I would like to point out really quickly that in these two examples we were finding horizontal asymptotes. Basically, when you have a function and when you increase x really large, when you make x really large, the value, if you get any value, then that value is your horizontal asymptote. So the definition of a horizontal asymptote is as follows. So the limit as x tends to infinity of f of x, if it equals a constant, say b, or if you have the limit as x tends to negative infinity, f of x tends to another constant, say a, either of these two, then you have horizontal asymptotes of f of x. And graphically that's something like this. Now that's something like this. So imagine you're tending x to infinity. So if like x gets like really large, this function will go to 0. You might have guessed this function is 1 over x, but I'm just writing the first quadrant. So as x gets really large, this fraction becomes 0. So this function has a horizontal asymptote. Well, I've just drawn this broken line to show the line of the horizontal asymptote. Now one method of solving limits is what's called substitution. So for example, if you have this question, limit as x approaches infinity of the sine of 1 over x, well, you can do a change of variables here. So you can say let t is equal to 1 over x, and when x approaches infinity, t goes to 0, right? So I can totally rewrite this question as t approaches infinity of sine of t, because that's what I've defined t to be. I mean, these two mean the same thing. Just change the variables, and when I change the variables, the limit needed to be changed as well. So yeah, you can solve this. This is easy. 0. You can just substitute that inside. So let's do a slightly harder example. The limit as x approaches pi over 6 of the sine of x minus pi over 6 over root 3 by 2 minus cosine of x. Now I'll remind you that, rather I'll give you a hint that those properties that we defined earlier, they were for, the sine and the cosine properties, sine and the tangent properties, my bad, were defined when, say, x was tending to 0, right? And we don't have x tending to 0 here. So what you might want to do is instead do a change of variables. Change of variables works like that also. So let x minus pi by 6 equal t, and when x approaches pi by 6, or t approaches 0. So I'm going to rewrite this quickly as t goes to 0 of the sine of t over root 3 by 2 minus the cosine of x is just t plus pi by 6, sorry. So I just want to quickly expand the cosine in the denominator. Sine of t over root 3 by 2 minus, so I'll write the formula, cos of a plus b is equal to cos a cos b minus sin a sin b. I'm going to use the same thing. So cos of t is cos t times cos of pi by 6 is root 3 by 2. Now this minus and this minus, they'll become a plus sine t, sine of pi by 6 is just 1 by 2. I'll just multiply it there. Now I just want to regroup the root 3 by 2 of the denominator. It's root 3 by 2 times 1 minus cosine of t plus sine of t over 2. And now I want to just factor out this 1 by 2 in the denominator. When it goes on top, it will become a 2. I'm going to convert this sine t into its half angle. So 2 sine t by 2 into cos t by 2 over, this is just 2 sine squared t by 2, 1 minus cos t is 2 sine squared t by 2 plus 2 sine t by 2 cos t by 2. Now I'll just go ahead and cancel this 2 sine t by 2 from everywhere. This is gonna just drop one power. Now I'm left with limit as t goes to 0 of cos of t by 2 over root 3 sine t by 2 plus cos t by 2. And when I substitute t is equal to 0, this thing becomes 1, this thing becomes 1, sine of 0 is 0, this thing will become a 0, and all we are left with finally is a big 2. Now before I go, I'd like to give you guys an exercise because this method's kind of new to you guys. So limit as x approaches a of x times sine of a minus a times the sine of x over x minus a. So since x tends to a and there's an x minus a term, this is a good candidate for substitution. So I'll just give you a hint. Let's say h equals x minus a. When x tends to a, h tends to 0. So when you do that substitution here, you'll have to use some trigonometric identities and then you'll get the answer finally. Now we move on to what's called the definition of E. And E is basically Euler's constant. It is approximately equal to 2.71828. Yeah, it's kind of transcendent. Okay, so now there is an identity here. Limit as h tends to 0 of 1 over h raised to 1 over h, sorry, 1 plus h raised to 1 over h is equal to E, which is Euler's constant basically. Or we could write this as limit as g tends to infinity of 1 plus 1 over g raised to g. That's again equal to E. Now if you've understood the last method properly of substitution, you might know if I just take g as 1 over h, then if h goes to 0, g goes to infinity, and you can basically write this as this. So this is the formula we're going to use now. So the first example goes like this: the limit as x approaches 0 of 1 plus sine squared of x raised to the cosec squared of x. Now it's quite simple really. We just need the reciprocal of sine squared on top, and if you know trig well, you might have already seen that. I'll just write it down properly. Over sine squared of x. Now as x goes to 0, sine squared of x goes to 0. So because there was like a single variable and the reciprocal of the single variable on top. Now we have like a sine squared. You need to show this. We need to show this. So we could also write our limit like this: goes to 0 of 1 plus sine squared of x raised to 1 over sine squared of x. This is equal to e. I did this because looking at the original identity, we had like a single variable, and then that variable was, in this case, it was going to 0, and we were raising it by the reciprocal of the variable. We were getting e. But we had a sine squared term over here in this example, and we need to show this for sine squared. I mean, it's a healthy practice. Now we'll do another example. Limit as x tends to pi by 2 1 plus 2 cot squared x raised to 3 tan squared x. Now from the previous example and even from the identity, it's pretty clear that we need the reciprocal of h on top. So in this case, we need the reciprocal of this term entirely. So we need 1 over 2 cot squared x on top, which is basically tan squared x by 2 on top. So I'm going to do some multiplications and divisions on top. X tends to pi by 2, 1 plus 2 cot squared x and tan squared x by 2, and as I said, we need multiplication and division. The original 3 times 2, so essentially we've only multiplied and divided by 2, and now this thing is just e. So you can essentially take the limit inside, because this is for all our purposes a continuous function. When I do that, this is basically e, because when x approaches pi by 2, 2 times cot squared x approaches 0, so it satisfies the identity as well. So this is e raised to 3 into 2, which is e raised to 6.